All right, good morning, you guys. Today we're taking on scale factor and similarity ratios. So the first part, we're looking at something that is review. We did this earlier on in this semester when we were talking about similarity. So here I'm looking at two triangles, and I'm telling you that they are similar, and I know that their ratio is 4 to 5. So here, just remember that when we're talking about scale factor, we've referred to that as K. So K, our scale factor, is the ratio of new to old. So if we're saying that that's a ratio of 4 to 5, we're saying that the ratio of new to old is 4 to 5. So here is my new, and here is my old. So if I'm applying the multiplier on my old to get to my new, that would be my directionality of it. So the old here is my pre-image, and the new is my resulting image. So if I'm applying a multiplier to this figure to shrink it down to be this figure, like go from this measure to this measure, I'm applying the scale factor as a multiplier. I'm multiplying the 5 by 4/5 to become 4. Okay, and then if I'm going in reverse, then I'd be multiplying by 5/4 to become the 5. So the directionality is really crucial. Which way are we going? So if we're stating a scale factor, then this is new to old. This is my new is my image, my old is my pre-image. Okay. So then the ratio of any sides would have the same ratio. These are sides here and here. So my side ratio would have to be 4 to 5. So any altitudes, so if I was to draw in that perpendicular segment that connects this vertex to this side right here and same here to here, they'd be in the same ratio as the scale factor, same as a pair of sides, 4 to 5. Okay, any medians, so if I found that midpoint right here and then drew in that segment, the midpoint right here and drew in that segment, again, it's a segment relationship. It will have the same ratio as the scale factor, as a pair of sides, as the altitudes, so also 4 to 5. Okay, my mid-segment, so if I had a midpoint here, and then connected, midpoint here, and then connected, my mid-segments will be in the same ratio as a pair of sides as the scale factor, also 4 to 5. And then perimeter, so if I added up all of the sides here, all of the sides here, and all of the sides are already in a ratio of 4 to 5, right, my perimeters, the sum of all of my sides, will have to have that same ratio too, 4 to 5. So here, just a little reminder that all segment relationships have the same ratio as the scale factor. Okay, and then area is different because area now we're looking at the space, right, that is covering this shape. So for area, we know it's always taking that scale factor and squaring it. We saw this earlier when we were talking about similarity of all of our 2D shapes. So area will be 4 over 5 squared, which is like 4 squared to 5 squared, so 16 to 25. Okay, so this first problem is really just a review of what we did first semester when we talked about our earlier this semester, when we talked about our 2D shapes, our two-dimensional shapes. We looked at our triangles, we looked at our squares, our trapezoids, parallelograms, circles, etc. So we know that any segment relationship right? Going to be the same ratio as the scale factor, but area will be the scale factor squared. So now we're going to extend that to our three-dimensional shapes that we're looking at right now. So here I've drawn out cubes. So here I've marked one side as 3, but I know that that means that all of their sides have to be 3, and all of the sides here have to be 8. And if I have my arrow going in that right-hand direction, then I'm saying that this figure is my old, my pre-image, and this figure is my new, my image. So my scale factor here, let me just write that out. So my scale factor K, the ratio of new to old, will be an 8:3 ratio. So if I take 3 and I multiply by 8/3, I would get this side as 8. If I took 8 multiplied by 3/8, I would get back to the 3 right here. So again, the directionality is key. All right, so remember, base edges here, all of the sides have to be 3, all the sides here have to be 8, so my base edges will have the same ratio, 8:3. My heights will be in the same ratio also, so 8:3. Okay, my diagonals, so if I connected this point to this point, for example, this point to this point, for example, well, my diagonals are segment, so same ratio, 8:3. So everything so far has been a segment relationship, so it's had the same ratio as the scale factor, 8:3. But now base area, the key here is area. So base area, well, I could even solve it. My base area here would be 3 times 3. My base area here would be 8 times 8. So what's happening, we're squaring it. So we can see that we're just taking that 8/3, squaring it. 8 squared to 3 squared is 64/9. So surface area, well, it's just 6 base areas. So if I have 6 times 9, and here I have 6 times 64, when I reduce that ratio down, it's going to be the same as the base area ratio. So my surface area, right, all of those collective surfaces together will be in the same ratio as my base area was. So I'm taking 8/3, squaring it. 8 squared to 3 squared is still 64/9. Okay, and then volume, right? Volume, we picture it like a fish tank, right? We're looking at the water that would fill up our fish tank. So what would our volume be? Well, here if I do length times width times height, which for a cube is just any side cubed, well, I can see that my volume will be over here 3 cubed, here will be 8 cubed, right? So I'm just looking at 8/3 cubed. So 8 cubed to 3 cubed, right? 8 cubed is 512, 3 cubed is 27. Okay, and then scale factor we already solved for, right? Scale factor is what we did initially. Our scale factor was the 8/3. So what we're really seeing here is that, again, any segment relationship has the same ratio as our scale factor. Anything with area is just the scale factor squared. And then volume is taking that scale factor and cubing it. All right, let's go to that next page. All right, so here on that second page, I just wanted to summarize what I just said out loud. So our scale factor, let's say that I define it with variables, so I can say A to B. So my scale factor is A to B, so that's going to be the same ratio as any sides, any heights, any perimeters, any diagonals, any segment relationship. So same ratio as sides, heights, diagonals, Okay, perimeter, etc. So again, just any segment relationship. Okay, and then the area ratio, we're just taking that scale factor, a to b, and we are squaring it, so it becomes a squared to b squared. So that would be true for anything that's area. And now that we're moving into three-dimensional shapes, that means it could be talking about base area, but it could also be talking about surface area. Okay, no matter what, the ratio will be a squared to b squared. And then for volume, right, as we just saw with our cube, we're looking at a to b cubed, which will become a cubed to b cubed. Okay, so a nice rule of thumb, you can think about it as, what parts am I looking at? Am I looking at anything with area? Then it's got to be squared. Am I looking at anything with volume? Then it's got to be cubed. Anything else will be the same as the scale factor. All right, so let's do some practice problems. All right, so the scale factor for two similar heptagons, so a seven-sided figure, is 5 to 9. So that's giving us, again, that's giving us the scale factor. So that's telling us that A is 5 and B is 9. So if the smaller heptagon has a perimeter of 123 centimeters, find the perimeter of the larger heptagon. Okay, so we need to figure out what's our perimeter ratio. And our perimeter ratio, right, is going to be the same as our scale factor. So it's going to be 5 to 9. So now I can build a proportion to be able to solve for my unknown perimeter. So I know that 5 is to 9, right? That is the ratio that I know that I'm building off of. That's my perimeter ratio, 5 to 9. And I know that the smaller heptagon has a perimeter of 123. I want to find the perimeter of the larger heptagon. So the way that I have my proportion structured is I have my small to large number, 5 to 9. So it has to be my small to large number for the perimeters as well. So my actual perimeter for the small one is 123. So small on top, large that I want to solve for on the bottom. Okay, cross multiply, and we get 5x is equal to 9 times 123 is 1,107. Okay, from here I'm going to divide both sides by 5. And I'm going to get that my unknown large heptagon perimeter is 221.4 centimeters. Okay, looking at B next. Here, if the larger heptagon has an area of 240 centimeters squared, find the area of the smaller heptagon. So here I need an area ratio. Area ratio. So I'm going to look at that scale factor that I had initially, and I need to square it. So 5 squared is going to be 25, and 9 squared will be 81. So there's my area ratio that I need to build off of to make my proportion to solve. So I know that 25 over 81 is equal to. So in this case, my large heptagon has an area of 240. So I have it stacked as small to large. So it has to be consistent over here, small to large. So I'm solving for the small. I know the large. So x over 240. Okay, go ahead and solve your proportion by cross multiplying. So we get 81x equals 25 times 240, so 6,000. And divide each side by 81. So we get that x is about 74.07 centimeters squared. All right, next up, example 4. So here we're starting with a surface area ratio. So that's our starting point. We have two similar right pentagonal prisms, and that ratio is 49:16. So since we were starting with an area ratio, we were given that the A squared is 49 and the B squared is 16. So if I take the square root of 49 and the square root of 16, I can see that the A value is 7 and the B value is 4. So my scale factor, the K, will be in a ratio of 7 to 4. All right, for A, if the larger prism has a volume of 450 units cubed, find the volume of the smaller prism. So here I need a volume ratio. So if I go back to my scale factor 7/4, I need to cube it. So 7 cubed is 343 and 4 cubed is 64. So there is my volume ratio. It's just taking that scale factor and cubing it. So now I need to build my proportion. So I know that 343 is to 64 just as. So in this model here, I have my large over the small. I have to be consistent here, large over the small. So we're told that the large prism has a volume of 450. So large over small, 450 over x. So now I cross multiply. I get 343x is equal to 64 times 450, and I get 28,800. So now I divide each side by 343, and I get that x is about 83.97 units cubed. Okay, next up, for B, if the smaller prism has a side length of 12 units, find the side length of the larger prism. So I need a side ratio. Okay, and a side ratio will always be the same as the scale factor. So my scale factor is 7 to 4. Okay, so I need to build my proportion off of that. So here I know that this is 7 to 4. Okay, just as the smaller prism has a side length of 12, so I have it stacked as large to small, so I need it large to small here as well. And my large, right, the large is what I don't know, so I have x and I have 12. Okay, from here I cross multiply, so I have 4x is equal to 7 times 12, which is 84, and then I divide each side by 4. And I get that x is equal to 21 units. Okay, let me push up last two. Okay, so here we're starting off with a volume ratio. So that means that my ratio of my two similar right hexagonal pyramids, 27 to 8, well then that's giving me that the A cubed is 27 and the B cubed is 8. So if I take the cube root of 27, I see that A must be 3. If I take the cube root of 8, the B must be 2. Okay, so then I know that my scale factor is a 3 to 2 ratio. Okay, so in A, if the smaller pyramid has a base area of 57 square units, find the base area of the larger pyramid. So I need a base area ratio. So So I take that scale factor and I square it because I'm dealing with area. So 3 squared is 9, 2 squared is 4. So my ratio here for my base area, for any area, is 9 to 4. Okay, so now I build my proportion. 9 is to 4 just as. So the smaller pyramid has a base area of 57 square units. We want the base area of the larger pyramid. So how it's stacked is large to small. So it has to be large to small over here as well. And I don't know my large, and I do know my small. So it's x over 57. So cross multiply. 4x equals 9 times 57, so 513, and then divide each side by 4. So x is going to be equal to 128.25 units squared. Okay. All right, next up, here, if the larger pyramid has a slant height of 23 units, find the slant height of the smaller pyramid. Okay, so slant height ratio, got to start there. So slant height ratio. Okay, it should be the same as the scale factor, so 3 to 2. So building my proportion, 3 is to 2 just as. Larger pyramid has the slant height of 23. We want the small pyramid. So I have it stacked as large to small. This needs to be large to small as well. So 23 to x. Okay, cross multiply, and 3x equals 2 times 23, so 46. Divide each side by 3, and we get that x is equal to 15 1/3 units. All right, we are done for the day. So a nice little extension of what we did back in our similarity unit earlier this semester. We just now extended it into 3D, right? We covered all the different 2D shapes and now push it into 3D as well. All right, that's all I have for today. Hope you guys have a good rest of your day.